All right. I'll hand it over to Chandler to start the tutorial. Chandler, if there are any links that people can click on, just add them in the chat or put it up on your slide so people can go there for this section of the tutorial. But
Okay.
with that, I'll turn off my camera so you can take it over.
Great, thanks. And thanks for everybody that stuck around for this tutorial. The goal here is to really give you a kickstart on how to launch a simulation in Feast and look at results from it. So I'm going to start by going through some of the resources that are available online. So that includes documentation of how the code started, the doc strings that are available within the code, and a user guide that we've developed. And then I'll move on to providing a live tutorial in a Jupyter notebook to see how the code can actually be run. So I'll share my screen here, screen number 1. And so the first thing, I'm going to bring us to Arvin's webpage. So if we go to that webpage, he has a link here that's dedicated to Feast. And so here you can see the slides from the webinar today, and later we'll have the recording posted on this website. So this is a great homepage to just see all the resources for Feast compiled in one place. So I'll go ahead or Arvin, maybe you can add that to the chat, just the link to the homepage for Feast.
Yep.
Great, thanks, Arvin. In particular, I want to highlight here this link to the GitHub repository. So if we click this link, it should bring us right to the, oops, that's not the one I meant to click. This is the GitHub repository. So if you're not familiar with GitHub, it's a platform that allows developers to post their software online, and anybody can access it and look at the code and even download it to your own machine to run simulations. And so this is where we're storing Feast. In addition, GitHub allows you to store multiple branches or multiple versions of the same software. So if we click here, you can see a few different versions that we have posted. So Feast 3.1 is the version we're releasing today. The master branch is the version that will continue to update as we go on. And you can even see the branch Alan's been working in on quantification methods, but that is under development. So if you do try to work with that, you will find bugs there. But Feast 3.1 is the version we're working on now, and the master is generally the most up-to-date branch that you can look at. So there's several resources that are included in the GitHub repository that I want to highlight here. The first is the README. So if you scroll down, the README file is displayed on GitHub. And so this gives an introduction to Feast, a brief history of how the code has developed over time, and links to the Jupyter Notebook that we'll look at in a minute, and a few references to various resources. So this includes papers that have referenced Feast, as well as the webinar that we gave about a year ago when we released version 3.0. And down at the bottom here, we list a few documentation resources. I want to highlight the user guide next. So the user guide is available through GitHub as well. It's labeled here, Feast 3.1 user guide. And you can open it right in your web browser. So it just takes a second to load. And this user guide is meant to be a good place to start if you're new to Feast and want to learn how to launch a simulation. So we've got a table of contents. We have a history of the modifications. So this is hopefully very useful if you've been working with Feast previously and now we've released a new version and you want to see what's changed. And then we move on to talking about the model structure. So I'm going to jump down to this section to highlight the structure of the software itself, and that'll be helpful when we go to create a simulation. So I'll scroll down to the model structure section. or in fact, I think there's, let's see. Okay, so at the highest level, feast defines a scenario, and the scenario contains everything that's required to run a simulation. That includes a gas field object, so that object defines all the infrastructure for the simulation. One or more LDAR programs, so these are the actual leak detection and repair programs that we want to represent. And finally, time settings for the model, for the simulation. So these include the time resolution and as well as the duration. So I'm going to show a few of these UML diagrams that summarize how the software is structured. So we have a scenario as the highest level data structure. And one scenario can have many leak detection repair programs. That's indicated by a little star here. And a scenario can also have exactly one gas field and exactly one time object. So now we'll zoom into the gas field class in more detail. So a gas field is made up of a collection of one or more sites. So again, we've got the star here to illustrate the one or more relationship. And a site contains one or more components. So if you recall from the first part of the webinar, a component is defined by its emission characteristics. So these include things like the emission production rate, a path to a distribution of emission sizes, many different parameters that you can look at on your own time. Then in addition to these infrastructure items, we also have an emission data object. And the emission object actually stores the properties of every emission that occurs during the simulation. So that includes emission rate, the site where that emission occurs, the component where that emission occurs, whether or not an emission is repairable, when the emission begins, when it ends, and how much it would cost to repair that emission. So all these types of data are collected into a single gas field object when you're setting up a simulation. Next, we'll move on to leak detection repair programs. So this is another one of these UML diagrams, and I'll walk through some of the key details that I want to highlight. So at the highest level for this, we have the leak detection repair program. It has a one-to-many relationship with the detection method. So you can define multiple instances of detection methods and pass them all into one leak detection repair program. The detection method has many types of results that can be associated with it. So I'll give some examples of that in the Jupyter Notebook tutorial. But just know that a detection method is associated with many results data that are saved. This type of arrow that's pointing to the left is illustrating an inheritance relationship. So we have these three different classes of detection methods that are supported by feast, and they all inherit methods from this parent level of the detection method. So these are, I mentioned these earlier in the webinar. We can represent a site level monitor, a site level survey, or a component level survey using these classes. In addition, leak detection repair programs require repair objects, and each program maintains its own emissions data object. So this is similar to the emissions data object that the gas field stores, but it's modified by the leak detection and repair program during the simulation. Specifically, the time at which some emissions end will be changed by the LDAR program. So if you're looking at this on your own time, you can see some more details about how results are saved. And finally, we can get to how to actually launch a simulation. So I find this flowchart helpful to remember how to set up a simulation. So the first step is to define the components that you want to simulate. And so components need an emission rate distribution as well as a repair cost distribution. And so these both get passed into the components when they're defined. Then these components are combined to create sites. So you can define many different sites. And finally, once you have the sites defined, you can create the gas field object, which contains all of the sites. And the gas field also requires, or may use, meteorological data, as well as it needs to know what time resolution the simulation will be run at. On the other side of the diagram, we can define the leak detection and repair programs. So that begins with defining repair methods. Those are passed as dispatch objects to, and by dispatch object, I mean an action that a detection method can take if it detects a leak. So those are passed into detection methods. And you can also define detection methods that have other detection methods as a dispatch object. So for example, if you have a plane-based survey, it might have an OGI camera ground crew as a dispatch object. So finally, once we get these detection methods defined, we can pass those into a leak detection and repair program. So at this point, we've defined the time settings for the simulation, the leak detection and repair programs, and the infrastructure contained in the gas field. So we pass all three of those into the scenario. And once we have the scenario defined, we can run the simulation and finally interpret the results. So interpreting results, is a significant task in and of itself. So I want to highlight a couple of details there. The first is that Feast, in this version, we allow you to save results in one of two different methods. The first is a pickle method. And in that case, we take this scenario object after the simulation is run and simply pickle the whole object. And so that's useful if you just want to look at a couple of iterations and see minute details about how the emissions behave during that simulation. And right, so sorry, so with the pickled result, you can see the really fine details of how a simulation progressed. In contrast, if you want to save, you can also save results in a JSON object. And in that case, Feast will pull out sort of high-level results from the model. And so that's really useful if you're running hundreds or thousands of Monte Carlo iterations. If the pickled results files will be fairly large, and so it'll take a lot of time to look at those results if you're looking at hundreds or thousands of them. Whereas the JSON files are much smaller, much easier to load and look at results, but they don't store as much detail as the pickled files. So that's something you can set when you run a simulation. And then interpreting the results will require somewhat different functions depending on the method you use to save the data. And so that's an overview of what's available in the user guide. I'll check in here and see if there are any questions. I don't see anything new in the Q&A, but feel free to add questions as we go along if you'd like. So this is, remember, we're still in GitHub here. Oh, it looks like there may be something in the chat. Okay, well, feel free to let me know if there's a question we should address, Arvind.
Yes, actually, one just came up in the chat. Regarding the Monte Carlo simulation, how long does it take a Feast user to do? So can you just address a little bit on the timing and the number of Monte Carlo simulations we need for this?
Yeah. So there's a few details to answer that question. So the amount of time that it takes to run a simulation is going to depend on the time resolution that you choose, as well as the type and number of leak detection and repair programs that you want to simulate, and the number of sites that you're simulating. As an example, in the preprint that I alluded to during the webinar, we were simulating one tiered detection program and one OGI program. And a single iteration of that might take around a minute. And we're looking at 300 iterations, I think, in the results for the majority of the figures in that reference. That being said, in that paper we were actually, or if if you take a look at the preprint, many of the results are based on I think 400 different versions of these LDAR programs. So once we're we're simulating 400 different LDAR programs at once, then that slows down the simulation significantly. And continuous monitor methods, as they're represented right now, tend to slow down simulations a little bit too. We'll see that in an example in a little bit. The good news is that Monte Carlo iterations can all be run in parallel. And so as long as you have the computing power, the running many Monte Carlo iterations doesn't need to take the amount of time it takes doesn't need to grow linearly with the number of iterations you're interested in running. Okay, and I see a question here about from Jason about standardization. So the comment is that any fixed settings, e.g. standard upstream gas field with standard meteorological conditions, would help compare performance of different technologies. So I think it's a really interesting point. We've moved away from having default, or I think that would be equivalent to a standard gas field in the software itself, because I think it can be, well, the results of the simulations are really sensitive to the details of how the emission simulation is set up. And so if we by creating a default, there's a risk of the results seeming to say that one technology is better when in fact it's only better in this particular case. But in a different basin, the results could be very different. And so we've moved away from having a default settings in the model. That being said, if there was, say, a regulatory agency that developed a standard set of sites for a particular location, then that could be really useful and could be used within Feast. So I think I'll go ahead and move forward with the tutorial here. It looks like Clay and Arvin may still be answering some questions in the question and answer panel, but I'll keep moving forward. So that was the user guide we just went over. The next resource I want to show you is also available in GitHub. So if we just go back up to the highest level directory here, I want to show you this docstrings PDF. And so this document compiles all of the docstrings that are stored in the software itself. And so if you're familiar with Python, these are the comments that you'll see if you use the help command in Python on one of the classes or methods in Feast. So there's a couple useful things here. The first is I find this table of contents actually very helpful if you're trying to find a particular method or class within the software. You can look at this table of contents and it lays out how the various modules are related to each other. And then if we scroll down, we can see an example of what the docstrings look like. So abstract detection method is a class, is a module, and it contains a class called detection method. And so we have a brief description of the class here, a list of all the parameters that are required to initialize that class, and then each method associated with the class is documented as well, with a similar structure of listing the parameters, a description of the method, and any values that are returned. So I won't go through this in any more detail than that, but I want you to be aware that it is available as part of the software package. And so finally now I want to bring us to the Jupyter Notebook tutorial that I've mentioned. So there's a link to it right here in the README file. So if you get to the GitHub homepage and scroll down, you can see a link to it here. And there's a couple of different versions. If you just want to log on really quickly and aren't looking to save any of the changes that you make to the notebook or any of your results, you can use this first link, and it may ask for a username, but you can just enter any name you like in the field there to access the notebook. And then the second version requires you to have a GitHub account. And as long as you have that GitHub account, you can use it to log in, and we'll actually store the changes that you make to the notebook for you on a Harrisburg server. I wouldn't use this this is still meant to be like an educational tool, so you can use it to explore the model, run some things, and maybe make some changes in the notebook and come back the next day. But we're not guaranteeing that we'll store your data indefinitely. So if you're trying to use this for research or to answer a question for your company, then it would be important to make sure that you run this on your own machine and have a robust way to store the data. So with that caveat, I'll launch this notebook. The first time you log in, it should ask you for your GitHub credentials, but I've already logged in on this browser, so I didn't need to. So this is the first page that will come up. This is the parent directory of Feast. So we can open that up, and right away you should see one highlighted in green. That's the Feast tutorial. So we can open that tutorial, and this is now running on a Harrisburg server, and it's live. So you can make any changes you want. It'll save it within your own account. So you don't have to worry about breaking the model or anything like that. And if you're not familiar with the Jupyter Notebook, they're a platform that allows you to incorporate both text and code into a single file. And so these each sort of section is known as a cell. And so we have a couple of cells of text here, and then the first code cell imports the packages that we're going to need. So you can see I'm importing Feast here, and then I'm also importing a few packages that will be useful for plotting or creating arrays that we might want to pass into Feast. So to run a code cell in a Jupyter Notebook, you press Shift-Enter. So I'll go ahead and do that. And that imports the packages. And now if you can think back to the flowchart I showed a little bit ago of the various steps to setting up a simulation in Feast, we're going to go through each box in that flowchart and run a simulation live here. So the first step is defining components. So here you can see I'm calling in Feast the component class. I pass in a name for it, a path to an emission distribution. So this is you can see that I'm looking in this example data directory that's included in the Feast repository. So if you download the software, it will include this example data directory, and you'll be able to see the type of data that Feast uses. And so I give a path to an emissions data distribution that will specify the size of emissions. And then I specify a few other parameters here to detail the properties of this component. And finally, I want to highlight this last one, base repairable, that indicates whether emissions from this component are vented emissions or fugitive emissions. So if that's set to true, that means it's repairable. That means I can call it a fugitive emission. You could also set that to false, and then the emissions would not be repairable, and they would be considered vented emissions. So I can press Shift-Enter here, and now I've initialized this component object. In practice, I would want to initialize many of these different instances of components with different properties to make up a single production site. But for this example, to keep it simple, I'm just going to make a production site that only has one type of component on it. And I do want to clarify that a component object in Feast could be used to represent, say, connectors and valves. Like you could use one component to represent a collection of different types of infrastructure, or you could use one Feast component object to represent a collection of physical components, as long as the statistical parameters you set for the Feast object capture the properties of the full collection of physical components. So with that in mind, we've got a component defined. We can now pass that into a site object to create our first production site for the simulation. So here I'm going to say there's 2 wells in this site. I'm going to say there's 650 components per well, and that's not just on the wellhead, but the total number of components on the site. So that's going to be a total of 1,300 components. And I'm going to call the site class in Feast. So you can see I'm looking at Feast. I'm looking in the emission sim modules directory at the infrastructure classes module, and then finally the site class itself. And in order to initialize this site, I have to give it a name, and I have to give it a dict of components. So inside the dict, I've got fugitive, that's the type of component I just defined. And then I have the number of those components, which is going to be 1300 in this example. And then finally, I'm passing in a copy of the component object that I defined above. And so this structure is really flexible because you could easily add a second type of component, put a different name here, a different set of numbers, and a different set of parameters. And you can define as many of those components as you want and collect them in a single site. Next, I'll set the time parameters. I'm going to say a simulation time of 1 day. The time units in feast are days, and then the end time is 365 days later, so that's a year later. So once I have a site defined and the time object defined, I can create a gas field object. So again, here I'm going to define a dict that contains all the sites. I've only defined one site for this example, but in principle, you could have many of these. And one note I wanted to highlight is you can specify the number of identical sites. So in this case, I'm simulating 100 instances of this single site that I defined earlier. So, but in addition to specifying that number of this type of site, you could also define different sites with different numbers of those sites within the gas field. So finally, I've got this dict of sites defined. I have the time parameters set up. And now I can define a path to meteorological data. And those three inputs are used to define a gas field. And I just realized I think I haven't been running these code cells as I went along, so let me do that. So it's a shift enter, shift enter, shift enter. Okay, so the next step is defining leak detection repair programs. The first thing I'm going to define is a repair object. The only parameter that we can specify for a repair object is the delay between when a detection is made and when the repair occurs. So this is in units of days, and I've set it to 3 for this example. So I'll store that object. And then the next step is defining detection methods. So I'll define an OGI detection method first. So if we look in this function, you can see I'm calling the component survey class. So we know an OGI camera is looking at individual components, and it's a survey-based method, so that's why we need to call this comp survey class. And then there's a collection of parameters that we need to set. You can look through these on your own, but a few highlights I want to make are, first, in order to define the probability of detection curve, we first need to define a set of emission rates. So that's here. And the units in feast are grams per second for emissions. And the second line I need to define here is probabilities. And so this is the probability associated with each of the emission rates defined in the array above. So we're saying for an emission rate of 0.5 grams per second, or there's a bit of a unit conversion here. So this is kilograms per day that's then converted to grams per second by this factor. But the point being, for an emission rate that's less than this first entry, we have a 0% probability of detection. And then for an emission rate of 2 kilograms per day, we have a 50% probability of detection, and so on. So we pass those points into a detection probability points parameter and a detection probabilities parameter. And then the final detail here is that we need to specify which variables we're referring to. So we're going to refer to the flux for this probability detection curve. And we're going to look at if the flux is somehow changing within a single time step, we're going to look at the mean throughout the time step. And so that's the detail I wanted to highlight for the OGI object. The next example here is also an OGI object, but with one change. Here I set the survey interval to none. So that means that the survey is never going to dispatch on its own. This is useful if we want to have an OGI ground crew that's dispatched as a follow-up action to some other program. So that's how this will be used in the example simulation. The next, I'm going to define a plane-based survey. So here we're looking at site level emissions. So I call this site survey class. And the input parameters are similar with a few subtle differences. The speed here is defined as sites per day, whereas for a component survey, they're defined in components per hour. And the cost is based on the cost per site, rather than I believe it's dollars per hour for a component level survey. So a few subtle differences, but generally the same types of parameters included here to define a plane-based survey. Next up, and the last detection method I'll look at is a continuous monitor. So there's a few differences here. I mentioned in the webinar earlier that rather than a probability of detection, we're going to look at a time to detection. And so that's defined in with the same type of data structure as the probability of detection curve. But it's just that now the units are a time to detect in days rather than a probability of detection. Another issue I wanted to highlight here, though, is you can see here where I specified points, whereas in the previous example, it was a one-dimensional array. So if we look here, we have a one-dimensional array defined for points. Now I'm defining a n by 2 dimensional array, or an n by 2 array. So the n refers to the number of points we're looking at, and the 2 refers to the number of independent variables we're considering. So in this case, we have 2 columns, so we are considering 2 independent variables. To see what those variables are, we have to look at the detection variables parameter. The first one is flux. So the first column here refers to emission rate. So by flux, I mean specifically emission rate. And then the second column is wind speed. So the second column here is referring to wind speed. And that's really where the mean parameter becomes important. So the typical meteorological year data that feast relies on is hourly data, but I defined a time resolution of 1 day. So we're going to look at the mean wind speed during a day to compare it to the time to detection function. That, alternatively, we could also consider the maximum or minimum wind speed during a day. So there I can initialize that continuous monitor. Now we're almost ready to run a simulation. We just have a few more steps. So first we need to combine these detection methods that I just made into an LDAR program. So the first one's pretty easy for defining an OGI survey. It gets a copy of the gas field, and then it just gets the OGI object itself. And that's it. I'm passing in a copy of the OGI object here simply because I find that it's a good practice to avoid a case where I accidentally pass the same detection method to multiple LDAR programs. Doing that is passing the same detection method to multiple LDAR programs, will cause an error in feast because the queue for sites that program is supposed to survey will be shared across multiple LDAR programs, and they'll be updating it incorrectly. So the next, I'm going to look at one more example of an LDAR program here, and that's a plane-based survey with OGI follow-up. So in that case, I define a dict of the 2 detection methods that are included. So the plane survey, and then you'll see here, I'm just passing in the dispatch object for that plane survey as OGI. And that's because I know the dispatch object for the plane survey is an OGI follow-up ground crew. So once we have that tech dict defined, we can initialize the LDAR program in feast, pass in the gas field, and pass in that tech dict. And it's a similar process for the continuous monitor. Finally, once we have all the LDAR programs initialized, we can combine them into a single dict. That's passed into a feast scenario here. And we're finally ready to run the simulation. So I'll kick this off. It'll take a minute or so to run. I'm sorry, I think it's running faster than I expected, which means that I forgot to run this code cell. So let me run that, and then we'll make sure that the continuous monitor is included here. So I'm going to kick this off again. And you can see it's printing out the status as the simulation completes. So that's specified by this variable within the run command. So you can, if you set display status to true, it'll update you as the simulation runs. I'm also defining a dir out variable that tells the program where to save results. So it's going to save it to a directory called tutorial results. If that directory doesn't exist, it'll make it. And if there's already files in that directory, it will name the file that it produces realization, and then with an integer that follows, that's 1 greater than the number of files already in the directory. And then finally, I have the save method here, which I've set to pickle. So that means it's going to pickle the scenario and save it as a pickled file. So the simulation's almost complete here. I'll just give it another second to save the result, and then I'll show you how we can look at results from it. You can tell that it's still running because I've got the star here next to the cell. So there, it just completed. It should have saved a result. And now I can use a plotting function. So feast includes just 2 plotting functions for looking at results. I think they're useful to just see what the results look like generally and see if there's any obvious errors. But you'll likely want to define your own plotting functions to do your own analyses. So the function I'm going to call here is within the plotting functions module. It's called time series. And it'll create a time series of the results file that we just generated. So it should look similar to this, but a little bit different because the model is stochastic. Oh. So that looks like there's an error in the simulation somehow. It's likely an initialization problem. I don't think I'm going to go into that in any more detail here, but so what I think likely happened is I may have forgotten to run one of these code cells, and that's resulted in an error in the results here. But rather than debug that here in real time, I'm going to go back to the example that I was showing earlier. So I'm just going to look at a different realization or different results file here. And this is more what I would expect the results to look like. So here we have 4 different scenarios being simulated. The light blue across the top is sort of what we're simulating without a leak detection and repair program. The red is the plane-based survey, so it's generally below or always below the no LDAR program. And you can see that there's a steep decrease in emissions at the beginning of the simulation, and then again about halfway through, and that's because we're deploying a survey every 180 days. The next curve here is the dark blue. That's a continuous monitor, and so you can see it's reduced emissions further, and also that the emissions reach sort of a new stable state without the rapid decreases associated with a particular survey that we see in the survey-based methods. And then finally, we've got the OGI survey. It accomplishes a very deep reduction in emissions at the beginning of the survey, but then new emissions occur over time and approach the original condition. One note here is we see this sort of sawtooth pattern, and that's because we're simulating 100 sites, and it takes less than 180 days for a survey to get through those 100 sites. If we were simulating more sites, at some point, the OGI team might be working continuously, and then we wouldn't see that sawtooth pattern anymore. So I've got I guess 2 more things I wanted to show here, and then I can stop for questions. So that was an example of looking at a single iteration. Now I want to look at multiple iterations. And I'm going to go back up here and just make sure that I've initialized all these cells correctly. So to do that, I'm going to restart the kernel and just go through and run each of these in turn. I don't need to run that simulation, and this should then work. So I've shown you how to set up the entire simulation. And now I'm going to show how we can run many iterations at once. So I'm using this multi-processing package, and that will allow me to run many simulations in parallel. So I'll import those packages. And then here I'm referencing this function called make iteration. It's in a tutorial helper file. You can see that in the repository. But the takeaway is that it's actually just copied all of the functions that I already showed you up above and put them into an external file, which makes it easier to run these iterations in parallel. So now I can launch the simulation, and you can see it's running 10 simulations all at the same time. I've excluded the continuous monitor so that this will complete a little bit faster. And I wanted to highlight here that you can see that these iterations are not occurring in order. And so that shouldn't be a surprise. It means that the parallel computation function is working as we would expect it to. So while that completes, so you can see it's starting to get onto the second set of 10 here. I'll speak to how we can plot results. So the second plotting function that Feast has included is called this abatement cost plotter function. So you can access it again in the same module as the time series plotting function. But here we pass in a directory rather than an individual file, and Feast will automatically read all of the files in the directory and combine them into one plot. It takes a few input parameters, including the global warming potential, which is set to 34 in this example, the discount rate, so that if you want to include a net present value analysis, you can set a discount rate here. And if you want to include the value of the mitigated emissions, that is, if you want to account for the value of the gas that's not being lost due to the leak detection and repair program, you can set a value for that gas here. But once we have those parameters defined, you can see that the simulations have now all completed, all 30 of them. And we should end up with a plot that looks like this, where we have that shows the distribution of mitigation costs across the two different types of technology. The final piece I wanted to show here is using this JSON save method. So this is very similar. Again, I'm going to run a simulation and save it as a JSON file. It'll take a few seconds to run the simulation. It's a bit faster because I'm not including a continuous monitor. And then it outputs a file in the JSON format. So to read that, I need to import this JSON package from Python and load the file. And now I have this results file stored as res. So to look in that, I can never remember what the various keys are for that file, but it's structured as an enormous dict. And so by looking at the keys, you can get an idea of what's contained in it. So the first step at the highest level, I can look at the keys. I've got an OGI camera survey, a plane-based survey, and the null or sort of no leak detection and repair program method. And the null is actually, it's really a useful result to store, particularly in the future when we're working with co-simulation with a process-based emissions model. This null parameter will show the original emissions produced by the process-based model before the leak detection and repair program is applied. So we can go into each of these parts of the DIC to get more detail. So for example, if we look at the plane, we see the emission time series event. So this will be a time series of all the emissions in the simulation. Then we have the event time series, which is only the vented emissions. And if you're interested in the fugitive emissions, you can subtract the vents from the total emissions. There's also the cost of repairs under this LDAR program. And then these three, it might be a bit confusing because I've got plane again here under plane, but that's referring to the first level is referring to different leak detection and repair programs. And then this next level is referring to the detection methods within that program. So here we can look at, say, the OGI camera crew that's dispatched as a follow-up action from the plane-based surveys. And we can see what data is available there. So it includes the cost of deploying that team, the count of how many times it was deployed, how many times the operating envelope failed due to a site level condition or due to a field level condition. I don't think I've mentioned that in the webinar before, but the operating envelope can be set so that there may be some conditions that are site specific rather than that apply to the whole field. So that's in the documentation if you want to see more details about that. So that concludes the tutorial. We're just about out of time, but we've got a few minutes if there are any more questions.
Chandra, there's one question in the chat asking about where you enter the meteorological axis for the probability of detection surface.
Yeah, let me come up here. So if you want to include a meteorological parameter in the probability of detection surface, it's the same format, whether you're looking at a continuous monitor or a survey-based method. And therefore, whether you're defining a time to detection surface or a probability of detection surface. But it's passed into the object under this time to detect or detection probability points parameter. And when you pass it in there, you can pass in this multidimensional array, and you specify which parameters the columns refer to with this detection variable dict. So if you're referring to wind speed, you enter that into the dict here as the second entry, and it will refer to the second column. So that's where you would specify the met data in the probability of detection function.
Chandler, so the points are the sort of XY grid, right? And then the Z value is the time to detect days in this case, or the detection probability at each of those intersections, right?
Exactly, yeah. All right, if there's no more questions, we can wrap up here. So again, if you're looking for more information, Arvin's website is a great place to go. I think that link is in the chat already, and you'll also be able to find contact information there for us. There's also a feast.help@gmail.com if you're working with the code and have code specific questions. And so those emails to that address go to me or Arvind or Alan. So thanks again for your time, and I'll pass it to Arvind to see if he has any concluding remarks.
Thanks, Chandler. Perfect timing. I just want to thank everyone who's been with us here for the past 2 hours on this webinar and the tutorial. On behalf of the Colorado State University team, as well as the Harrisburg University team, we thank you for your attendance here on this webinar. As Chandler said, I want to reiterate, we'd all like to work with you to develop this model further, do technology testing at METEC, and get us forward on methane emissions detection and mitigation. So feel free to email any of us. There's a separate feast-specific help email if you have technical questions, but we'll keep you updated as we update models, have new features, and we'll reach out to you if we have any specific requests. But as always, thank you so much for coming. And unless you have any pressing concerns at this moment, we'd sign off. And once again, thank you all for coming.
And thank you to the Colorado Energy Research Collaboratory for hosting the webinar for us as well.
Happy to do so, and I'm glad you all came. Thank you, everybody.